Okay, welcome to the VLSI devices. This is the very first lecture of our VLSI devices. So let me introduce the course. The course number is EC4313, and actually it has also dual code SE3101, but right now there is no junior level students in the Department of Semiconductor Engineering. So actually all of you guys are coming from EC4313, I guess. And it has 3 credit, and every Monday, Wednesday in the first lecture slot we will have the session. And my name is Sung Min Hong, and okay. So in order to attend this course, actually you had to attend the semiconductor material and devices. Its code number is EC3206, or an equivalent course. So some of you are coming from graduate school, so you never attended that course exactly. But if you had similar courses, then it's okay. So okay. So this is not the very first course for semiconductor devices. So this is the second one. So that's the reason why we need prerequisite. So if you cannot understand the basic stuffs in this course, then please stop learning this course. As a textbook, I will use Professor Tower's book, and it has actually the latest version available is the third edition, but I will use just second edition. And if we have a new materials added in the third edition, then I will just add it to this year lecture contents. But I guess that more and less the physics is given, so second edition is enough for our purpose. Okay. And in the case of resources, you can find these lecture materials in the following GitHub repository. So let me just do it together with you. So how can you do that? First, search the repository. So here you can type the name of repository and VLSI devices 2025, and this is spring semester. So when you just enter, then maybe you can find my repository, then click it, then you will have, of course this is just almost empty readme.md, and here you have lecture material. Usually I just upload my lecture material just before the lecture starts, so maybe midnight. So you can download it before joining this morning session, then you can just watch it. But I guess that in this classroom, offline classroom, maybe this area is more better for watching this PowerPoint file screen. So I recommend you to guys in the next time, so please move to this part, because I'm trying to avoid the use of small letters because I have a low vision, but I'm not quite sure whether you have also good enough vision to see these small letters, so please. And yes, what else? Okay, and I will use just LMS system for announcement. So then if I make any announcement, then I guess that an email will be sent to you automatically. But please check our LMS system occasionally. And we have a homework submission. But as I will tell you very soon, although we have homework assignments, then it does not, or they do not contribute to our total score. So this is just for your own study, so not counting to your final score. And also you have a YouTube channel. So let's go to you youtube.com and okay. So let me just try to my name. I'm not quite sure whether okay, you can see my channel. So here you can see the playlist, and that playlist, our playlist is here, VLSI devices, and currently our present lecture is being recorded, and later you can watch this video again and again and again. So I think that is quite helpful for you to make the your own study on our stuffs, because I guess that this material is a little bit advanced, so maybe it will be difficult for you collect all necessary information out of a web or something like that. So I hope that maybe our recorded video can be work as a good resource for your own study. Okay, and grading and policies. So attendance is 10%. So every morning I will just check your attendance, and yes, that will be counted as a 10% of your entire score. And midterm examination and final examination, 40% and 50%, that counts 100%. And you find that there is nothing others like homework score. I will give you some homeworks. However, they will not contribute to the total score. It's just for your own study. But I guess that if you cannot solve homework problems, then you cannot solve the examination problem. So please try to solve all of the homework assignments. Okay. Okay, so unfortunately, I have a business trip to Hong Kong next week. So due to my business trip, lecture 2 and lecture 3 should be given as a form of recorded videos. So they will be available the normal lecture time. So Monday 9 o'clock and Wednesday 9 o'clock on my YouTube channel. So then in order to show your attendance, please leave your own comments in that videos. Okay, then I will just say that okay, this guy attended that course. Please try to watch the entire video, not just to leave your message. Additionally, almost close to the end of our semester, week 15. So I have another planned trip to the Kyoto, Japan. So I'm not quite sure I have to prepare another recorded video or not. That really depends on the lecture progress. So that will be decided later. Okay, so this is the announcement, and now let's go to the main contents. So before starting our main lecture contents, so if you have any question, then please let me know. Then okay.
다음 주 수업은 그러면 저 시간대에만 볼 수 있는?
Oh no. So that will be available always. But so I will just check the attendance Monday and Wednesday. So if you come to there, for example, Thursday and leave some messages, but that will not be counted as your regular attendance. Okay. Good question. Any other question? Okay, then let's go to the today's lecture, and I hope that today's lecture will be quite short, so I will try. Okay, so let's come back to my own lecture material. Let me just okay, scale down. Let me just go to my own lecture material in 11 years ago. So at that time, I took the course called as digital design. Maybe some of you guys already attended that course, and this is just showing how to design a basic logic circuit. And you know, this slide was taken from my own lecture material. At the time, I wanted to show you that, or not exactly you, the other students, how much the microelectronics has been evolved dramatically. So that was the very first CPU, and it is called Intel 4004, and it was first released on 1971. 1971, even before I was born. And at the time, we had 2.3 thousand transistors. So actually this chip was designed by two guys, one leader and another Japanese supporter dispatched from Japanese company. So they did it after spending a few, not few, but several months. They were able to design this one. And at that time, 2014, the state-of-the-art CPU was there. Yes, this one code name was Haswell, I guess, and it has, although it has its long name, official name, but it was called as Haswell, and it was released in 2013, already 12 years ago from now on, and it had 1.4 billion transistors. So please try to consider the difference between 2.3 kilo and 1.4 billion. So you can see that, not exactly, but it is close to the 10 to the 6 a million times more transistors in a chip. So that was my own lecture material in 2014. So I told my students, wow, electronics has evolved quite a lot. That is amazing. Then, now 11 years have passed once again. Then what will happen to our industry? As of 2025, so we are in the March, what is the state of the art device or chip? It is no longer a CPU. Nobody talk about CPU anymore. And unfortunately, it is no longer an Intel chip. Nobody talk about Intel anymore. Then this guy. This is Blackwell. This code name is Blackwell, and it was released in the last year, and it has 208 billion transistors. So please think about the difference. So about 10 years ago, I told you that 1.4 billion, more than 1 billion transistors. Wow, that was the story. However, after 1 decade, now we have almost more than 100 times more transistors in our chip. That is the evolution of our chip industry. Semiconductor industry is rapidly changing still, although it has already shown and proved so much improvement. So then what is the magic behind it? How can we increase the number of transistors so drastically? So please have a look at this diagram. This diagram is the top view of our chip. So it's not real chip, but just imaginary one. And you can find that there are two different lines, two different types of lines. One is, horizontal ones, and one is vertical one. Then here, this horizontal line is corresponding to the semiconductor, and this vertical line is corresponding to metal. When these two lines are meeting together at a certain point, then that point, this point becomes a transistor. So by just crossing these two lines, then you have transistors. How can you do that? We will study this one in this lecture. However, the magic is we have drastically increased number of transistors. Actually, when we compare the die size, here die size means that the area of silicon consumed by a chip. And when we make a comparison between this Haswell, this guy, and Blackwell, actually there is a few times difference in its chip size or die size. It means that NVIDIA chip is consuming wider area space, 3 or 4 times. Wow! However, the difference of number of transistors shown here is more than 100 times. Then how can we integrate more than 100 times more transistors into just 3 or 4 times wider space? That is shown here. So Haswell was fabricated with Intel 22 technology, and this 22 technology is quite an amazing one because that was the very first generation of FinFET technology. Before Intel 22 technology, the technology, our transistor was just a planar MOSFET. And at this time, they switched to the bulk FinFET technology, and it is a story of a long success, more than 10 years. And at that time, per square millimeter, 1 millimeter by 1 millimeter, when you consider this a small silicon chunk, you can integrate 16 million transistors in it. It is already quite a large number. However, now, so Blackwell is fabricated with a variant of TSMC N5 technology. So not exactly N5 technology, but that technology is not open to us. So we have no exact number. So we can guess a similar thing. N5, this is the main technology or the base technology. And with this base technology, per square millimeter, we can integrate 130 or 140 million transistors in it. So it means that between this time period, people have invented some ways to integrate more transistors into the same silicon area. So that is the magic behind it. So scaling down, make it smaller, that is our magic. So think about this one. Here you can see two different Lego creations. Here we have a very beautiful and wow, maybe it cost quite a lot. And here you can see this one has its own name, My First Dog. And this is not exactly Lego, but this is from Duplo for imprints. So let's say that your boss come to you and ask, build this Hogwarts castle for display. And if he or she gives you just Duplo blocks, tons of Duplo blocks to you, and make it, then what will happen? If you are a genius in Lego creation, but you cannot build this beautiful one with Duplo bricks, in order to make it, at least you have to have a normal Lego brick. Otherwise, your realization of a Hogwarts castle with Duplo block will size not this big. It will just take our entire room, lecture room. So it is really important, even though you have creative idea and best designing skill, but in order to make a beautiful creation, you need good building block. That is exactly same for our chip industry. If you wanted to make a certain application processors or GPU, you have very good idea, but if you have to use, for example, 180 nanometer technology, or if your technology is just 1 micrometer technology, you never get such kind of a state-of-the-art device. The performance of your chip is determined by two factors: how much your technology is performing, and also how good is your design is. So we are now talking about this technology part. So that's the reason why, for example, Apple or NVIDIA always try to make some negotiation with TSMC, because they wanted to have the state-of-the-art device technology to make the best product. If you cannot secure the most advanced technology, then although your designers are working very hard day and night, however, the result cannot outperform the competitors' ones. So that is quite important for survival in this chip industry. So now I wanted to start from this concept, layout and 3D structure. For example, this is the example of a NAND gate. I hope that all of you guys already understand what NAND is. So NAND is not of an AND gate, and if you have two inputs A and B, only when you have A equal to logical 1 and B equal to logical 1, then usual AND will give us just 1, and not of this AND becomes 1. Simply speaking, in this NAND gate, only when you supply 2 VDD voltage to your terminals, input terminals, then you will have the output voltage close to 0. That is NAND gate. Then, as a circuit designer, you can think about the layout. This is layout, and this is nothing but just a top view of your chip. When you have a look at your chip from the top of your chip, then of course it actually doesn't look like this, but it is an imaginary concept of our chip seen from its top. And you know that using this layout for designers, then we can build this kind of a three-dimensional structure. So for designer, chip is just looking like this, and to device engineer, chip is just a collection of these kind of complicated three-dimensional structure. Here you can see different colors. Different colors mean different materials. Here you can see that some blue-gray one. This is corresponding to your metal, and this is for sending your signal or taking your signal. They are connected in a complicated way, but you can see that there is one-to-one correspondence between your layout and three-dimensional structure. Where can you find the correspondence? For example, here you can see this shape. Then this shape is corresponding to the metal shown here. Please try to find another one. for example, here you can see this part is connected to the ground voltage, the 0 voltage, and you can see that here there is a metal, and that is actually connected to the ground voltage. So if your transistor's signal is connected to this ground voltage, then you will have the output logical 0, and this is corresponding to the correct operation of NAND when you have both of 1 and 1 for your input. And also you can find this is for metal, and here you can see that how can I say, the purple one, or light purple one, and that is corresponding to the silicon. So actually switching operation actually happens in this silicon part, but not in this entire silicon part, but just underneath gate contact. Then where can you find the gate contact? Now you can see there is a relatively dark purple region, and this is corresponding to the gate. So silicon underneath this gate part is working as a switching part, the channel region. So by changing the electrical conductivity at that point, we can just connect one node to the other, or we can make the disconnection between them. So as a device engineer, our goal is from this layout sent from designers, then we wanted to make this three-dimensional structure quite well, and its performance should be good enough to satisfy designers' specification. Okay. Since it is a little bit difficult to see the details of this one, I have prepared a similar figure once again. This is a little bit further simplified one called as inverter, and inverter is just not gate. If you give 1 as an input, then you will have 0, and if you have 0 as an input, then you will have 1. This is realized by this three-dimensional structure. Then how can you make this kind of a logical operation? Here, this part is attached to the voltage source corresponding to VDD. So the voltage you can expect, the maximum voltage you can expect in a system. And here you have the connection to the ground. Ground is regarded as the reference of your voltage. This is 0. And here you have two different metal lines, and this metal line is used as your input, and this metal line is used as your output. Then now situation is quite clear. Here we have two given voltages, and what we wanted to do is just to select the voltage of this output metal. Then how can we select or set the voltage of this output metal? One way is, okay, this metal is electrically connected to the VDD, at the same time electrically disconnected from ground. This is one case. If that happens, the output voltage will be just VDD. You can easily understand that situation. On the other hand, if we make the disconnection between VDD and out node, and at the same time, if we make the connection, electrical connection between output node and ground, then our output voltage will be just 0, and this is just output of our inverter. And then the requirement is the ability to change the electrical connection between this output node and VDD and output node and ground. How can we electrically control this connection? That is done by this input metal, and by changing this input metal voltage, actually this metal is connected to these blue regions, and these blue regions are another metal. Although this guy is metal and this guy is also metal, they are made of different metal elements. And by selecting this way, we can make electrical connection and disconnection, or disconnection and connection between our output node and other two given voltage nodes. That is operation of our circuit, CMOS circuit. And although it has quite a huge size, but please try to find out the most critical part in this entire system. My question is this part is so important for your application? It's not. Or is this part is so important for your system? It's not. The most important part is, only we can say, is here, here and here, because by changing the electrical conductivity at these 2 points, we just connect or disconnect our output node to VDD or ground. So although we have a certain system called as a semiconductor chip, but the most important part is just underneath the gate metal. So we will concentrate on this small part, and by understanding the operation at that part, maybe that is possible to more or less describe the behavior of this system properly. Of course, nowadays I have to say that my view up to now is so much simplified, oversimplified one. Nowadays, every part plays quite critical roles. So, but at the beginning, we can say that these parts are most important. Okay. Okay. So then let's go to the. So therefore, we need to, in order to make more and more transistors, saying that more and more transistors at a given area, it means that we need to make smaller and smaller this structure. If we make this structure quite big, then we cannot integrate more transistors. But if we can make this structure quite small, then we can integrate so many transistors into it. So we have a clear roadmap for scaling our transistors. In this context, in our, how can I say, in our lecture course in this semester, when I say scaling, means that reducing the size of something. So scaling roadmap means that how can we reduce the size of our transistors? That is scaling. And roadmap means that there are some competitors in this chip fabrication industry. For example, you know, there are some Taiwanese company and there are Korean company, USA, American companies. They are competing. And although they are competing, but at the same time, they need to adjust their development phase. So you are doing quite well. I will just copy. And they wanted to make a certain agreed progress of our technology. This is called as a roadmap, and this semiconductor industry is quite good to make a roadmap. For several decades, they have made roadmap for next technology development, and amazingly enough, they always achieve that roadmap. Oh, when they say I will do that one by 2025, then they did it. So that is a really amazing thing. So where are we now? Currently, we are living in 2025, and the current node is called as N2 node. So N is I'm not quite sure why we have N, using N. Maybe N is regarded as a nanometer or node, but we have no idea. But anyway, this number 2 is corresponding to 2 nanometer node, and say that although there is nothing related to 2 nanometer, but it's like a brand name for our current technology. We are currently in the era of 2 nanometer node, and we will move to now A technologies. So the A is corresponding to angstrom, but once again, there is no real angstrom scale devices, but we will move to in that way. So please have a look at these numbers. 2025, and our roadmap just says that at least 2035 we have a clear view. In next 10 years you have already given journey, so you will see those you will see all of those achievement. And from this part, I have to say that it's not that clear, but anyway, thinking or remembering the achievement that they have made, then I guess that maybe we can make this these technologies available to the young guys, even younger than you. So we never give up in this scaling. But why we don't give up? It is quite simple. The winner will take tremendous economical advantages. So right now there is one winner in this industry, TSMC, and TSMC is gaining not only economical advantages, but it is also related to some very important geopolitical implication. So since TSMC is located in Taiwan, even something can happen. So since this is so important, at least if you are quite close to this competition, then you cannot give up. Once you give up, then the game is over. Let's think about this one. If Korea stop developing the newest technologies, then what will happen? Or if USA stop developing new technology, what will happen? That already happened to some other countries like Japan, and they are trying to do it once again. And European countries, they don't have even FinFET technology in entire European continent. Their most advanced technology is just planar MOSFET, and by establishing a joint company between TSMC and EU, they are now trying to introduce the very first TSMC technology into the European continent, maybe Dresden in Germany. So simply speaking, since state-of-the-art device technology is so important, so I think that nobody can stop here. So we have to go on. If you don't give up the many important economical or other advantages. Okay, so The next one will be maybe next technology will be maybe CFET. It is not available in mass product, so currently we are a little bit away from this technology, but it is almost certain that technology will move to this direction. And you can see that this is the CFET is a device which is stacks NMOS over PMOS. So I assume that all of you guys already understand what is an NMOSFET and what is a PMOSFET. So am I correct? Or you never heard about NMOS and PMOS? So if you don't, in my opinion, actually, if you don't understand what is NMOSFET and what is a PMOSFET, then maybe it would be better to stop here, because we have prerequisite course. So anyway, so this CFET is stacking two different devices. So currently our MMOSFET and PMOSFET, these two different devices are built in side by side. For example, when you have a look at this layout, in this layout you can find that this part is corresponding to your PMOSFET, and this part is corresponding to your NMOSFET. However, CFET try to just stack NMOSFET over PMOSFET. Then please try to imagine what will happen. Here PMOSFET, and previously there was an NMOSFET, but now it is just placed here, and it means that in an ideal case you can expect twice more transistors in a same technology. Of course, life is not that simple. The maximum gain we can achieve from this CFET technology is not like 2 times, maybe 1.5 times is the ideal one. But anyway, 1.5 is still quite amazing number, so we will move to this direction. So here you can see that already industries like Samsung, TSMC, Intel, all of these companies are fabricating the prototype of a CFET, and this is the TEM image of a CFET. Where can you find the transistor actually? So here you have silicon. This is silicon, and this is silicon, and here you can see this is silicon, and this is silicon. And what is the size of this silicon? Vertical thickness, it is about 5 nanometer. And what is the size along this direction? It is around 10x nanometer. I'm not quite sure whether that is really 12, but it is around 10x nanometer. So this is extremely scaled, and you can see that there is one channel and two channels. These two channels are assigned for our NMOSFET, and these two channels are assigned to our PMOSFET, and they are vertically stacked and working as an inverter eventually, not right now. And this is a more clear view, although this is not realistic one but just a graphic, but you can see that those numbers, the eventual CFET will look like this, and its length scale is 12 nanometer, 5 nanometer, something like that. So eventually, so from one end to the end, the opposite end, there will be just 42 nanometer long. Right now, in our current technology, like 5 nanometer technology, this length scale is about 50 nanometer or even longer. It means that after 10 years later, we will have about 20% shorter distance. 20% is not that attractive, because we are spending more than 10 years to get just 20% reduction. But please note that now we have made CFET technology, so folded one, so we will get even higher aerial efficiency compared with the currently available technology. So that is the expected future. But today, or in this semester, we will not talk about CFET, because in order to fully understand the operation of a CFET, first of all, we have to start from the planar MOSFET, all the time technology. Okay, up to now, I have told you about the scaling in terms of transistor area. How can we make it small? But making small itself is not the only way or the only reason we wanted to make a scaling. At the same time, we must consider other two equally important factors, like power and performance. So now let's say that power is just fixed and performance is just fixed. Means that although you can make your transistors 10 times smaller in terms of area, your power consumption is not improved any further. Then what will happen? So previously you had a chip size, given chip size, and there was a power consumption, and number of transistor was just one transistor. Now you can integrate almost 10 transistors. Okay, good. Then if your power figure is not improved, then what will happen? Your chip will spend 10 times more power. So now think about this one. Compared with Haswell, Blackwell have more than 100 times more transistors. So if we do not get any kind of power efficiency, then roughly speaking, we have to provide 100 times more power to operate our state-of-the-art GPU compared with old-time CPU. So it's not affordable. So to every normal person like us, the amount of electricity you can get is quite much limited. So although you feel that I can use my electricity freely, it's only because the amount is quite low. So if you wanted to make so I wanted to use that nuclear power plant for my own purpose. Can you say that? So nobody will not accept that kind of request. So power, electricity is quite precious resources, quite a limited one. So building a system without reducing the power consumption is not feasible. So therefore, what we do in reality is, when we move from one given technology to the next technology, for example, from N5 technology to the N3 technology, scaled one, then we usually expect this kind of achievement. For example, smaller area. Of course, we are now integrating more transistors. At the same time, here important one is, and at the same time, the speed of your chip is 23% improved, so faster. And also at the same time, your energy efficiency is improved. This is not or and or, but the all of these three conditions should be satisfied at the same time. This is really amazing one. Usually we have an engineering trade-off. If you get something, then usually you have to sacrifice the other. That is life in many cases. However, in the semiconductor industry, they always wanted to get, in terms of performance or these electrical properties, they always want to get most of it. At the same time, reduce the size and improve power efficiency, and even faster chip can be made by introducing new technology. So then what is the real driving force for this kind of tremendous effort? Why engineers are trying to make this amazing technology, even though we already have quite a good technology, is if your company can provide the best technology in the world, then you will just take a monopoly. Your chip or your device will dominate the world, and you can just say any number you want to have, any cost. So that is the real situation happening right now in the world. So that's the reason why people are really trying to improve the performance. So sometimes I say performance, so there are two different words. So when I say just performance, sometimes it's like electrical properties or characteristics. But for more specific context, when I say performance, this is more related with maximum frequency of your chip can operate. Okay, so performance is sometimes regarded as the speed of your chip, and at the same time, this graph shows, or this figure slide taken from TSMC blog, and it means that the opposite view. Here, TSMC provides three different options to the designers. One is area scaling is not that high, just 15% reduction. However, you can get even much faster 33% speed increasement. There is one option, and the opposite option here, then your area reduction is 36% area reduction, but speed improvement is just 11%. And now you also have an option to compromise these two extremes. So your area reduction is in between, or and at the same time your speed improvement is also in between. Yes, this is a really balanced one. Why do we have this kind of options for designers? For designers' sake? No, actually, in former times, 10 years ago, 20 years ago, our chip makers did not provide such kind of options, because they did their best, and improvement was just here. It was not that difficult. Of course, that was difficult, but compared with today's competition or difficulty, at the time, achieving this smaller device at the same time faster device was not that difficult. It was achievable. But now it is almost impossible to arrive at this one within given time period. So that is another trick to announce our next technology. These guys having certain trade-off. If you wanted to have even smaller chip, then actually you have to compromise your performance. And if you just keep the area, then of course you can have a high performance chip. So it means that we are now facing some difficulties for the technology development. I guess that this is the last slide that I have. So then how the device engineers can achieve this amazing thing within short time period? Time given to them is usually 2 years. Within 2 or at maximum 3 years, you have to develop a next generation technology and smaller, faster, and more power efficient one. Then how can they develop this this amazing job? And their trick is they know various ways to improve the technology. They understand what is the critical point to determine this factor. If we change this region a little bit, then maybe that will change the electrical property of our transistor. And even before they do, they know. But how they know? They are educated. They know the device physics. So this course is for growing device engineers. So I hope that this course will be quite useful if you wanted to know more deeply about the state of the art devices. Okay, today's lecture is more like a conference presentation, but this is the end of this kind of presentation. So when you watch our lecture 2 or lecture 3, you will find that tons of numerical expressions will occur. But that is the main body of our lecture. In order to, the reason why I prepared this image is, he is an alchemist. He does something looks like magic, but inside it, what is the principle of this alchemist? It is just movement of atoms, and if we can predict the properties of these atoms, then we can do something like magic. Quite similarly, device engineers are achieving amazing jobs, but they do not make it by just praying to God. So they know, they are educated, and their rule is just understanding numerical expressions. They have to know the equations and formulas and rules, and that is quite a tedious way to become a device engineer, at least in terms of understanding. Of course, the real engineer should be working in the company, so I hope that you have the chance to make that happen. Okay, so thank you for your attention to today's lecture, and I will just wrap up today's lecture, and if you have any question, then please let me know, so I will try to answer as much as possible. Any question? No? Okay, so then thank you, and see you next Monday. Okay.